Hello, this is Dr. Christy Lukes, and this is the solution to Exam 2 for our Thermo 1 course. So now let's look at problem 6. In this one, we are the manufacturer of a steam turbine that's designed to operate adiabatically, so Q will be 0, and at steady flow. We have a test that expands steam from 250 degrees C and 500 kilopascals, and data is given for that, to 150 kilopascals. Now that's not enough information, but we have a selection of data at 150 degrees or 150 kilopascals. We know that the mass flow rate is 3 kilograms per second, and the power output is measured to be, so that means it's the actual value it was measured, and that's output, so it's negative 1200 kilowatts. And what we want to do is find the process efficiency of the turbine. Now, for a turbine, the process efficiency is going to be the actual work over the ideal work, or we could do it as power. Okay, and if you do a first law assuming negligible kinetic energy, potential energy, and we've said Q is 0, then what we're left with is that the power is going to be H out minus H in, for these two cases. Now the inlet state is given and it's defined, but the outlet varies depending on whether it's the ideal or the actual. Now I can actually mix these two definitions, and so I could say that the actual work or actual power, and to do that it would be the mass flow rate times HE ideal minus HI. So you see how I've taken these and I've used the original definition of efficiency for the actual process because we were given a quantity, and then I was given, I'm going to use the first law for the other piece. Now the problem here is I know that this is negative 1200, and I know that m dot is 3 kilograms per second. The problem is that I don't have HE out, or ideal. But this is volume of 0.4743, H of 2960.1, so this is my H in. U and S is 7.27 kilojoules per kilogram Kelvin. And then I have some choices here. And if you look at them, one has a delta V of 0. One of them has a delta U of 0. One of them has a delta H of 0. Excuse me, I marked the wrong one there. Okay. And then we have one that has a delta S of 0. If my ideal is reversible and adiabatic, then it's isentropic. So delta S equals 0. So S out equals S in. Therefore, this is the piece of data that I'm looking for. And so therefore, this is the exiting enthalpy for my ideal case. So therefore, the efficiency is negative 1200 kilowatts, 3 kilograms per second, times 2713.0 minus 2960.1. So negative 1200 kilowatts over negative 741.3 kilowatts. Now, okay, if you actually do this math, what you're going to see is that we get a number that is, in this case, 1.62. It's greater than 1. And we've been told that the efficiency was supposed to be a number between 0 and 1. Well, the problem is I've given you a scenario that is impossible. In fact, what happened was I had a typo here on my power. I did not mean to put 1200 kilowatts. I had changed the problem from another one I had used before, and I didn't change all of the values. So I do apologize for that, but so this would be impossible according to the second law.